So hopefully this time it will actually record. Pretty sure it will. So the first thing I want to do in class today is open up some questions, those of you that have all read very carefully through the first project and even tried stuff with it and tried opening the data and plotted the data, and you did a few things to get started on the project, right? Okay, and so of course now everyone has a million questions about it. And obviously we'll talk about how the k-means clustering works. That's a main topic for today. But also I just want to field any questions that you have before we get into that. So anybody have any questions about this project and what we're after, or anything I can ease your mind about to start with?
I'm confused on what some of the commands are in like a little sample code.
Okay.
Like what is like
in this piece?
Dot what was it, projection 3D, does that make the 3D?
Right, so in here we're importing matplotlib to be able to plot anything, importing NumPy. We're opening a figure, and what it returns is basically like a figure object, an object that is for that figure, and then I can get the current axis of the figure. That's what that is. And then AX is an axis object. And the input argument is saying that I want this to be a 3D projection, because by default your axes are going to be 2D axes. So when you do regular plots, it's going to be two-dimensional. So here I'm saying I want to get the current axis, and I want that to be a three-dimensional projection. Okay, and then I use linspace just like MATLAB. I define some x, y, and z values, and then I plot. Normally, if you're doing a 2D plot, you would do plot.plot. You wouldn't need to mess around with the axis, because the axis by default is two-dimensional. So if you're doing a regular 2D plot, you don't need to do anything with the axis, and when you actually plot, this would be plot.plot, the vanilla matplotlib plot. But instead, we're going to call the member function of the axis object that's called plot. So now it will plot on this particular axis that we've already defined as being a three-dimensional axis. And so now we're passing one-dimensional NumPy arrays with three different x, y, and z values to it to get a three-dimensional line plot. Okay, and then that's what this line is right here.
So what is T?
So T is transpose. Okay, and so that's a linear algebra term. And essentially, if you have a two-dimensional vector, a two-dimensional matrix, or an array, two-dimensional array, it takes the array like this and it flips it like that. Basically, it takes all the rows become columns and the columns become rows. And that is that's a way of just moving it in a different format. Okay, because right now, x, y, and z are horizontal vectors. By a 1D array is a horizontal vector. So when I v-stack, that's vertical stack. When I vertical stack three vectors, all of the x stuff is in a row, first row, all the y stuff is in the second row, all the z stuff is in the third row. And then when I transpose it, now all of the x stuff is in the first column, all the y stuff is the second column, all the z stuff is the third column. And that is how I have defined the way you should create this axis equal function to work, is where it's expecting data points in every row, and the columns are the x, y, z positions. So that's how I've asked you to create this axis equal function, which is something you will be writing. Okay? And that's a typical, we'll talk about that actually today too, is that format of every row being a data point and every column being the values in that data point, that's actually a machine learning standard way of representing data. That the rows are giving what we call the samples or the data points, and the columns are the features or the things about the information about that data point. So that's a standard format, rows being samples, columns being features. Okay? Yes, Will?
So what if we didn't link an axis equal function to take the graph to the right aspect ratio? What if we could use a different way to set the right aspect ratio? Is that okay?
I suppose so. Yeah, I mean, I want it to be, and you're just thinking you want to don't write a function and do something else instead of that function? Yeah, I mean, that's fine. Yeah. I mean, everything, what I want is I want this. And one of the things I've learned, maybe not necessary as much with you guys in a senior level course, is that a lot of students, they need some direction and they need a skeleton to go on. And I'm sort of telling them a good way to organize the code. But if you're wanting to do it a different way, that's fine. But we need to get it, and actually this figure I cropped it because, the way because we have to sort of spoof the axis equal because there is nothing like it. And essentially you have to make the z dimension, in this case, very large compared to what it needs to be, because in the x and the y dimensions are so much bigger than the z dimension in this particular case. So there's going to be a bunch of blank space above all of these things in your actual figure. Okay, like there, and I cropped that out when I photoshopped it basically in Paint. I cut out all that extra stuff so it wouldn't take up space in the figure. But here, this, it only goes up to, z goes up to as much as 2.5 plus 1. That's 3.5. So the largest z value is only at 3.5 here, but to make the axis equal, quote unquote, I had to have z go all the way up to 14. So your figure will look like this, where there's all this blank space in the vertical place. Because I've looked and I've scoured the internet, and there's a lot of people that have had this problem too, and apparently there's no solution to this in Matplotlib, and I found this workaround, and I started using it. So I don't know if you can find a better way that better than this, that'd be great, because I don't know of a better one. But if you want to organize your code differently, that's fine too. Yeah.
One more question. You do the axis fig.gca. I could never get that to work. I could do fig.add subplot, but I could never do the GCA.
Huh. Where you're returning, you're saying fig equals plot of the figure, and then you tried this code and it didn't work?
I got me based that.
Huh. Anybody else tried it? Did it work for you?
An error at 3D for me as well.
It gave you an error?
If it throws the error at 3D, you're not importing the axis 3D module.
I have a thing that mine is doing where when I'm...
Oh, maybe I am missing an import there.
It's the from...
I'm missing that's right. I'm missing an import there. You're right. All right, let's see. Yeah.
Mine's plotting it correctly, but it's doing a weird thing where in my from the toolkits import all that stuff, it's saying that it's
Yeah, this guy. This is what you need.
Why does it do that? Because here's doing it too, where it says it's unused, but as soon as you take it out, it breaks everything.
I know. It is really weird. I think it's because you never explicitly have on the right-hand side of an equal sign a function inside of there.
You never type in axis.
You never type axis 3D period and then using something from it, but rather you need it in there because AX in my example is an object of the class that's defined in this import. And if you don't import that, then you won't have that class definition.
Okay.
But if you did an axis 3D period something, then that warning sign would go away.
Because I was playing with it last night and then shut it down for a little bit. And it was like, oh, it's unused, so I erased it and came back to it later.
And it wouldn't work.
And it was just like, wait, it worked before I closed it.
So I need to add that import into the code. I'm not sure when I'm going to get a chance to do that, but I'll try as soon as I can. Otherwise, you can just write that down. That's it says MPL underscore toolkits.mplot3d space import space axis 3D capital A axis. When you put that in still, Will, it doesn't work for
I
you?
can never get the GCA to work. But I needed that for the add subplot.
I wonder if you have a different version of Matplotlib or something.
It's up to date.
You installed it.
Install the list that you gave.
Yeah. That's weird. Let me know if anyone else has a problem, and if you do, we'll have some sort of workaround doing subplot instead.
I just what I did for that fixie.
Right. It's always worked for me, but I don't know. It's finicky sometimes with the modules. All right. Other questions? Okay. What's interesting in many of these projects, the machine learning code is actually very simple, especially when you use scikit-learn. There's going to be like one line of code to call the kMeans clustering and you're done. You know, we're going to be learning all these other stuff around the side. How do you use that stuff? Some image processing techniques and these bounding box stuff, you know, so it's kind of interesting that the actual machine learning part of some of these projects is quite small. It's just how are we going to use the stuff? Okay? All right. So, I want to talk a little bit about kMeans clustering. This is an unsupervised. It's crazily simple. Okay, so one of the things about kMeans clustering is that you have to, at the beginning, decide how many clusters you want to be dealing with. So it's a little bit of a drawback, and I'll show you in a little while. There's lots of different clustering algorithms in scikit-learn. Some of them require you to know ahead of time how many clusters you want. Some do not. They require some other information that you need to supply ahead of time. This is what I'm talking about, a hyperparameter. So when you're using kMeans clustering, it clusters it all by itself, but you as the designer have to pick how many classes you want. Okay, so that's, like I said, it's an example of these hyperparameters that the human designer picks, even if the machine learning algorithm does all of its stuff on its own. So you randomly pick centers for your known number of centers, okay? And then for every point of your training data, you find which center is that training data closest to. And then that training data will belong to the cluster having to do with that center. Okay? So then you're going to partition all of your data into one of the centers that you have. And then what you're going to do is you're going to update the center. So here I've got a whole bunch of points. Here I have this center that I randomly picked. And then I'm going to update where the center is as the average position of all of the points that are closest to it. So I'm going to update that center. Well, it should be the middle of all of these points. You take the average of all the x's, that's the x point of the center. You take the average of all the y's, that's the new y point of the center. Okay? Now, once you move the center, it's possible that the closest distance is no longer the original center that you had because it was based on a different position. So once the center is moved, then you check which points are closest to which centers, and so points are allowed to change class or change cluster at that point. Okay, so then you identify what are all the points closest to these new centers. Then you update the center positions again. You update the center positions again. You update the center positions again, and you keep doing that until you have no change, that no point changes which center it's going to be in, because then this algorithm will just go on forever and nothing will change. Okay, so let's wait for it to start over here. Okay, it's going to start over now. Those are the random places. Move the blue. All the points are closest to the blue. Move the blue. Then update. Okay, so let's look at. I wish I could slow down a GIF. Maybe I should have turned this into a movie file, and then I could pause it. That's what I should have done. This is a GIF. So move the blue. Now recalculates. The red is closer to some. Move that one. Now the green is closer to some. Recalculate. And so the centers move, and eventually they end up where the clusters are. And that's, in the end, it's a pretty good solution. Okay? So maybe that's something if you really want to have a look. So this is a link to scikit-learn's documentation on clustering. Okay? And the one we're going to use is the kMeans clustering. Okay? And that's actually this one right here. So they have a couple different sample different clusters, and shows how well these how these different ones perform on these different situations. Because you can use all sorts. Take for instance here. here is, a whole bunch of data. I mean, it looks like there's one cluster. I mean, there really is one cluster there, okay? And if you run kMeans clustering where you're saying, well, there has to be 3 clusters, it's going to break that into 3 clusters, and this is the result that you get. If you say, I want to do kMeans clustering with 3 things, but there's really just a bunch of data. It's got to cluster it somehow. It's going to do something to it. Okay? So depending on how your data looks, you will get different results using different ones of these algorithms. Then down here, it sort of has a breakdown of the differences, and what are the parameters, what are the hyperparameters that you have to choose. With kMeans, you need to say how many clusters there are. Okay, this one here, it doesn't require a cluster, but there's some parameter called bandwidth. I've never used that one, so I don't really know what that means, but you have to supply a parameter that it's going to use, and you'll get different performance depending on what that parameter is. So that's the fine tuning that you do as a human designer to figure out how you want to make this work. Okay? So in the end, you can play around with some of these other ones if you would like. I'm really only, I'm expecting you to use the kMeans clustering. You're welcome to go and play with some of the others if you'd like. Okay? What I've done for the rest of the time in class today, and this is going to help us understand how kMeans works, but also give you a chance to understand the code, some Python code, if you're working on that. But here is some code that I've created to manually do the kMeans clustering, okay, rather than using scikit-learn. So I've done this by scratch, from the ground up. Okay, so what I've done is I've created a class called kMeans. It has a constructor which sets things up, and it has one member function, and that's fit. Okay, and what I've actually done here is I'm following the format of how scikit-learn works. Okay, because each one of those different types of clustering algorithms, there's a class that goes along with that, and you create a class, and all of those classes have this fit function. Okay, so I've created this to mirror what you get in the scikit-learn modules, and this fit function takes obviously itself. You have to have that in a class. But you don't notice it. But it also takes data, where data is a 2D array, where every row is a data point, and every column is a feature, where in this case it would be the X and the Y values. Okay, well, in the example I'm doing here, and what you saw on the slide, it was a 2-dimensional problem. Okay, there were 2 features, the X position and the Y position. In the project, you're going to have 3 features, the X position, the Y position, and the Z position. Okay, so you'll have three features rather than 2 in the project. This example, the code you see right now, I'm going to be doing it in 2, although I've written it so that it can work in any dimension. So you can run this thing in any dimension, but the example I'm going to do it is in 2. Okay, so then down here, well, all right, let me go ahead and run it. Okay, so here it has an animation, and every 2 seconds it updates it. So it had the stars were the original positions, and it's moving them to wherever it's going to be, and now it's done. Okay, now let me describe the data that I have. There's the cyan points and there's the magenta points, and they are how the cyan and magenta points are how they were classified by the kMeans. Okay, and the way I created this was with a Gaussian distribution. Okay, a bell curve. Okay, and the ellipses, they represent the standard deviations of this bell curve. Okay, so this guy right here has a smaller standard deviation in the x direction than it does in the y direction. This one here has a standard deviation that's the same in both directions. Okay, now what is not shown here is which class it actually belonged to. Now I'm pretty sure that this point right here was part of this class. Okay, but in the end, it got classified as this class. So that point, I'm pretty sure, is misclassified, and I'm pretty sure this point right here is misclassified. You can see there's actually some overlap of the standard deviation here. You know, these two clusters are relatively close. That some of them could overlap. Okay, I mean, of course, it's a Gaussian distribution. You know, you could have a point out here that belongs to this class. You know, it all just depends on the randomness. Okay, so you know there's going to be some misclassification here for sure, but it does a pretty good job. I mean, if this was perfect, then this center would be at exactly the center of this circle, and that center would be at exactly the center of the ellipse if the clustering algorithm were perfect. Okay, and if I had more and more data, it probably would get closer. Right now, there's 50 examples of each class. Okay, now I could change, for example, I could change the way the standard deviation of one of the classes. So I'm going to go ahead and change the standard deviation to be much smaller, so it's going to be a tighter situation. So now you can see these two classes, the random locations were both close to each other, then the cyan one moved, and now, you know, these two classes are much easier to discriminate between the two because they have, you know, that the magenta one has a much smaller standard deviation. So now I think probably all those points are correctly classified, and you can see the stars are more close to the center of those ellipses. Okay, but you know, some problems are harder than others. There's actual overlap of points, and there's really no good way to be able to get every point perfectly classified, okay, if there is that overlap. And so again, this goes back to the human designer choosing the features. You know, maybe there's another way for me to represent this data that is more separated. You know, maybe there's other information that I haven't considered in the features, and I, as the human, could go back and collect different information about the problem that would be more easy to separate them. Okay? But that's not, the computer doesn't do that, the human designer does that. So there's still a lot of influence that the human designer has over the performance of this machine learning system. Okay? All right. Now, let's look a little bit more at the code now, of how it works. So, here I have, I'm going to create my data. I'm going to do the NumPy V stack. That's a vertical stack, just like we talked about before. That takes an array and stacks them vertically. Okay, now they don't have to be one-dimensional arrays. It could be a two-dimensional array stacked with another two-dimensional array below it. Then just needs to make sure that both of these arrays have the same number of columns, or else you'll get an error. Okay, so what I did is I'm v-stacking the, I've got x stuff and I've got y stuff. Okay, and the NP normal, okay, that's going to be my x stuff. This is going to be the center of in my x position. That's going to be the standard deviation for the x direction. This is going to be the number of points in the x direction. Then this is the same for the y. Okay, the center location. Okay, you can see for this, the center is 3, 2. That's where the center for that one is. Okay, 3, 2 is the center. Okay, now again, this is what I'm talking about, how it can be really confusing with the way, the size and shapes and the data types that things get returned as. NP random.normal, it returns a one-dimensional array, 50 things in a one-dimensional array. But I want the x things to be in the column, so that's why there's a transpose on there. Okay, so I take the x, I take the y, I v-stack them together, and then I transpose that to get it to be in the other direction. Okay, so that's what's going on there. Okay, and I'm stacking together stuff for one class and stacking things for another class. And of course you can go in and look at the details and figure out how all that works. But this is a very common thing that you're going to want to do. You're going to be doing stacking of things together. You're going to might need to change, you know, which rows with columns. That's a very common thing. So the .t, you'll notice that is that's actually a data member. Okay? Because there's no parentheses there. Okay, so all NumPy arrays have a data member .t that is the transpose of that array. And then I'm just taking that and I'm sending that to VStack. So this basically is just building my data. Okay, and you can see I also displayed what the shape of that data is. The shape of the data, there's 100 rows and there's 2 columns. There's 100 data points, 50 of one class, 50 of another, and there's 2 features, the X and the Y position. Okay. Then I define some colors: magenta, cyan, gray, blue, yellow. And so I'm going to use those as the colors of the different classes. So this allows for 5 different classes. We're only using 2, so it's going to be magenta and cyan for when I plot things later. I'm going to set the number of classes, 2 in this case. Okay, and then I'm going to call the constructor of this my kMeans class. That's this class here that I've created, my kMeans. So I'm calling the constructor of it. I'm passing the number of things, the number of classes, and this is whether I want it to be animated or not. So you'll notice if you go back and look at the class, I have this Boolean that if it's true, it'll plot the animation. Sometimes you might not want to see the animation. You put false there and it doesn't plot it. So I just added that as an extra little feature. Okay. Then these, once I go through the code, these you can uncomment one of these, uncomment this, and now instead of using my kMeans, I'm using scikit-learn's kMeans. And you'll notice up in the top, I did import scikit-learn.cluster as clust. Okay, so all of the cluster stuff from scikit-learn now is under clust, just like I have np as numpy. So now if I run it, okay, it will not use my function, but rather the standard kMeans cluster in scikit-learn. Okay, and that's why I made my function be, mirror the interface that is. So this won't give you if I run this, it won't give you the animation, but if I close out this figures, we'll see I run it, and my figure now gives me the classification that I got with the scikit-learn's kMeans. Okay, but of course we're more interested right now in my own. Then there's some others. Spectral clustering, that's another one where you give it the number of classes, and there's agglomeration clustering, that's another one where you give it the number of classes. So those are 3 of the examples in that table and the documentation of the ones where you define ahead of time what the number of classes are. Okay, so here's where all the magic happens. Okay, and even the supervised learning scikit-learn functions, they also use this thing where you say the object.fit. So this is going to be a recurring thing. Even when you use a neural network or a support vector machine or Bayes, naive Bayes, you're going to do the same thing with fit, where you pass to it. In this case, you're only passing to it data because it's unsupervised. And again, samples in rows, features in columns. Had this been a neural network, you would have also passed another thing that gives the labels. What are the ground truth labels for each one of those samples? But in this case, it's unsupervised learning, so I'm only passing the data. I'm not telling it what the classes are. Okay? And then you're done. It's done. It did the machine learning stuff. It's over. Okay? Of course, I wrote the one for my kMeans. So then I also display one of the things that it has is that after it's done fitting, it has a data member called labels underscore. Okay, and that says what is the classification for each of the training data points. So you can see I also did size of labels and put the shape of that. That's a 1D. You can see here it's a 1D NumPy array with 100 things. So these are the predictions essentially. This is the kMeansClustering's predictions of what classes those 100 things are in. And it's interesting. I should have put a performance. I should have put a performance here. What percentage of them got classified right? Because the first 50 are class 1. The second 50 are the other class. I could add that in here to see what is how close are these labels. Are those labels? I guess I could put in here clusters, is it with an S? Yeah, dot labels underscore. So you can see, you know, it looks like, I don't know, is that 50 things? It looks like it might have gotten all of them correct. The first 50 being 0, the second 50 being 1s. And I guess that, I closed the figure. But it looks like it got all of them right.
There's some 1s in your 0.
Oh, yeah, there is. There you go. There's one. So that one's certainly an incorrect one. So at least one of them is incorrect. Good eye. Okay, so at least one of the points got classified incorrectly. All right? So then in here, let's see, where were we? Put it that. Then I go ahead and open my figure, clear the figure. I get the axes because I'm going to draw those ellipses. And it's kind of annoying. It's kind of annoying in Matplotlib to draw these ellipses. Again, you have to get that axis label from your figure. Then you need to create what's called a patch. And there's another import in here. There's an import Matplotlib patches. And so basically the way you draw different objects is you create a patch and then you add that patch to the axis. So I'm going to create a patch with an ellipse. What is the center? 3, 2. And then how big is the ellipse? And I'm taking getting the standard deviation, and it's going to be plus and minus, so that's why there's a 2 in there. The square root is in there because in the Gaussian function you're giving it the variance, and standard deviation is the square root of the variance. So that's why the square root is in there. So I've added the patch for the ellipse. I said what color I want that ellipse to have. That's black. I said it's alpha level. That's how transparent it is. So I made it 90% transparent, only 10% visible. And then I added that patch to the axis. And so that's why it looked kind of very light gray, because I made it transparent, black but transparent. That's why it showed up as light gray. Okay, and then I did the same thing for the other ellipse. Okay, then I'm going to loop through each one of my centers. In this case, there's 2 centers, so I made this be pretty flexible. If you wanted to change the data to have more than 2 centers in that, you could do that. You might have fun playing around with that. Okay, and then I went ahead and did plot.plot. That's the standard Matplotlib plotting of 2 dimensions, and you pass an array of the x values, and then I've sent just a single scalar. Matplotlib is actually kind. I don't think this would have worked in MATLAB, but I give an array of the x positions. Is that right? Am I thinking right? Where's that end? Oh no, that's not. Okay, so this is the row of the data. That's the row of the data. Which rows out of the data am I going to pick? Okay, and this is which column. And the 0th column is X stuff. Okay, then this is which rows, i.e. which samples I pick, versus the Y column, the Y values. So here is this is a 1D NumPy array of the X positions. This is a 1D array of the Y positions. Okay? And what I'm trying to do is to get the ith color. So what I'm doing is I'm asking, where are the cluster labels equal to I? So where are these labels over here equal to 0? Which is not going to include this one here, like Justin noticed. So it's only, that's going to have trues where all of the zeros are and falses where all of the ones are. Okay, so this is an array of booleans, and then I'm using NumPy where, and NumPy where is like find in MATLAB. It's going to return the index positions of where that boolean array is true. So it's going to return the index positions where all the zeros are. And then I'm using those index positions where all the zeros are, and I'm using that to index data. So that's all of the rows where there is a 0, when I is 0. Then it's going to be all of the rows where I is 1, for the second time through. And so then this is the one-dimensional array of X things, the one-dimensional array of Y things, and then I want it to be a small dot and have color I, where when I is 0, it's going to be magenta here. When I is 1, it's going to be cyan. Okay? So a lot of this visualization stuff, these are things you're going to have to get comfortable with because you're going to need to plot this stuff to be able to see what's going on. Okay? All right. So how do I actually fit this? Now this function looks really long, but actually a lot of it has to do with just the animation. All of that is just for plotting stuff. Okay, so this function is actually not as long as it seems. The constructor here, I set the number of centers. This is a data member. Num centers is a data member. Set that to n, which is passed in. Self.animate is another data member. That's set to what's put in. And if animate is true, I'm going to open figure 2 and set the figure as a data member so I can access its axis to be able to plot the ellipses. Okay? And then I'm going to go ahead and clear that figure if animate is true, and I'm going to be watching this as it trains. Okay? All right, that's the constructor. Then, in fit, the first thing I do is I'm going to create a NumPy array containing no specific values. I could have done NP zeros or NP ones. It would be the same thing. It would fill it with zeros or fill it with ones. But if you do NP empty, it will just be whatever junk happens to be in that memory location, which is what you're used to in C++. You declare a variable and don't set it to something, it has some junk value in there. So that's what NP empty does, is it's going to create an array with the number of centers rows and two columns. Okay, so in this case it's going to be a 2 by 2 array. Okay, where each row is a center, one of the two centers, and each column is either the X or the Y position of that center. Okay, then I'm going to go ahead and loop through all the centers. Okay, I am going to get a random integer. Okay, I'm going to get a random integer, and that's going to be my centers. So the ith center, both the X and the Y positions, is going to be these two values. Okay, so I don't know, there's probably a different way I could have done that, but basically I'm just trying to get random numbers in those 4 positions. Random number for cluster 1's X and Y position, random number for cluster 2's X and Y position. I probably could have done a randint and asked it to give me a 2 by 2 matrix of random integers. I don't know why I didn't think to do that, but basically I'm just trying to get random numbers for the starting centers. Okay? Then I'm going to go ahead and predefine the size of the labels that needs to be returned, and that needs to be a one-dimensional array with a number of samples in it. Okay, and remember the samples are in the rows, so data.shape0 gives me the number of rows, number of samples, which is 100 in this case. So I'm going to make self.labels underscore be an array of junk values that is 100 long. All right. Then I'm going to have a loop, and the loop needs to go as long as there's a change occurring, as long as some data point moves in its cluster. Okay, I want to go ahead and update it. Okay, and so I need to set change to true to make the loop start. Okay, I'm going to start off with my class list, and my class list, it's going to be a list that has the center for each of the data points. Okay, so each data point I'm going to identify which center is it related to, and right now it's going to start off as empty, and I'm going to go through each of the data points and assign it which center is it closest to. Okay, and I'm starting to run out of time if I want to get out of here a little early. But basically now I'm going to loop through each of the centers and initialize the list. I'm going to say that I'm going to put an empty list in there. Okay, so my class list, there's going to be a list of all the points in center 1 and a list of all the points in center 2. Okay, so class list itself is a list, and inside of there is going to be a list that has which data points, which index numbers, which rows are in each class. Class 1, the rows of things in that class. Class 2, the rows in there. All right, then I need to loop through each one of my points. That's each row, data shape 0. And I'm going to find the distance to both centers. And I'm using MATLAB commands here, MATLAB-like things where I'm doing both rows. The colon of the centers is being center 1 and center 2 in the rows. So I'm calculating distance is going to be the distance to each of the 2 centers. And then I need to find where is which is the center that's the closest. There's a min in there. And that index will tell me, is it class 1 or is it class 0 or class 1 that is my one that's closest. And then I'm going to add that index to the list that is for that particular class that's closest. And I'm going to update my labels. Okay, this is all just plotting. It's got ellipses and stuff like I've already talked to you about. Okay, now I want to go through, now I'm going to have a for loop here to go through each center because I need to update each center. Okay, so each center I need to update it to be at the position where it's the average of all its values. This is just for animation. Then here I'm going to find the new center by finding the mean of the x positions. Take all of the x values in that center, take its mean, that's going to be my new temp position. And then I'm going to check, is that temp position much different than what it was before? If so, I have had a change, so I want the while loop to continue. Okay? And then I'm going to go ahead and update my center to the new value. Then I'm going to do the same for y. Get the mean of all of the points in this center's y position. Check if it's changed very much from before. If it has set change to true, update the centers, and then go ahead and then that for loop ends. Go ahead and plot stuff, and then the while loop starts over again. Okay, so I update random positions. Okay, assign the classes. Find which class I'm closest to, and then I need to update each of my centers to the new positions, and then go over again. So it's a little bit, there's a lot of details in there, getting the syntax and all that stuff right, but the algorithm itself is relatively simple. Okay. So you can play around with this code. This code is up on D2L, so you can download it and check it out. Okay, you can try the different things here. There's also another set of data. Okay, and this set of data here, okay, is a little bit more difficult. So what I have here is that there's 10 times more data points in this cluster than there are in this one. Okay, and what you'll see is many of the times this doesn't work as well as you might expect it to. It's still moving, it's still moving, it's still moving. But oftentimes what will happen is that this center will stop somewhere in between, and some of those points and some of those points will be considered a cluster, and this is pretty much a failure. It's not very good. So there are drawbacks. It's not a magic bullet. If I have lots of points in one cluster and not very many in another, I could end up with problems. So here's the final result. Okay, where those are the two center positions. These things are the cyan are all classified together, but obviously these ones are supposed to be with the magenta ones. So like I said, machine learning is great, but it's only as good as you choose. You choose what the clustering technique is. You choose how many classes there are. You choose these hyperparameters, and you might make a bad decision, and even though the machine learning does exactly what it's supposed to, it might not be that great.